Hi, I'm Rebecca Meritz, and I'm going to talk to you today about SSL, also known as TLS. So what is SSL? SSL is a tool that helps us make the internet more secure. So by default, the way the internet was originally built and used by communication within universities, it was provided no security. It wasn't a priority. So it's something that's been tacked on after the fact. And TLS is the tool that allows us to make internet more secure. So when we talk on the internet, we're talking over the protocol HTTP, and we take TLS and we add that with HTTP, and we have HTTPS. And you're probably familiar with this to some degree, probably some more than others. When you go to your browser and you type in the URL, you might see either the HTTP or the HTTPS in the beginning, and maybe you see a little lock. So some quick clarifications. This talk on the wall was titled SSL, and I've used the words both SSL and TLS. It's the same technology, but TLS has superseded SSL. It's gone through many versions and revisions since it was first created. SSL version 1, 2, and 3, and now TLS version 1, 1.1, and the latest is 2.1. But they're both still in use. I'm going to try and stick with the newer TLS, but I may use them interchangeably. Another clarification is that SSL and TLS don't just provide security on the web. They provide security. It can be a protocol that can be added on to voice over IP or fax or securing your email or many other things. But in this context, I'm specifically going to be speaking about security and the web, but almost everything would actually apply in this larger context. Okay, so it's a tool for providing security. More specifically, TLS is a cryptographic protocol, and I'm going to talk more specifically about what those words mean. So cryptography, the practice and study of technologies for secure communication in the presence of third parties. And the key thing I want you to focus in there is secure communications. So this is a conference about security, but no one I've heard yet has really talked about what does it mean to be secure. And when we're talking about cryptography, there are three key aspects. There's confidentiality, so no one being able to hear exactly what exactly you're said. Authenticity, which is verifying identities. If you get a message, if you're going to a certain web page, like your bank, you know you're actually on your bank's web page. As well as integrity, ensuring safe transport. So if you see a message, you know that you're not missing part of it. So confidentiality, authenticity, and integrity. And we're going to get back to them a lot throughout the talk. Okay, cryptographic protocol. What is the protocol? It's a pretty simple word. A system of rules that explain the correct conduct and procedures to be followed in a situation. So the key word here is procedures. It's what you do in order to accomplish a task. So this is the protocol for hand washing. First you turn the water on, then you add the soap, blah, blah, blah. And the key thing to note here, what makes it a protocol, is it's the steps that you follow. It's not the specific time that you washed your hands right before you had fika. So here, now we're back to TLS. What is the TLS protocol? And these are the three basic steps of the TLS protocol. 1 is the handshake, 2 is the data exchange, and 3 is the shutdown. So how does this protocol actually provide us security? So how is this protocol, the handshake, and so forth, providing confidentiality, authenticity, and integrity? And throughout the talk, the plan is to build up why these 3 steps exist and how are they providing those 3 aspects of secure communications. And I'm going to start actually with step number 2, which is the data exchange. So when you go to a website, you are going to the client and you're saying, I want to see this particular site. And you send some data to the server of the web, and it says, here's your data back of the actual website you want to see. That's the data exchange. But how are we making that secure? And the structure of this talk is going to be different problems that we have in security and then the different technologies that TLS is going to use in order to solve those problems. So the first problem is one of confidentiality during the data exchange. The way the web is built by default, anyone can very trivially see the data going over the wire and see what sites you're looking at and the contents of them. So what is the first solution to this confidentiality problem? And that solution is symmetric encryption, also called private key encryption. So as you can see here, we'll start with pretend you're the client. So you're the person going onto your browser and you're saying, I want to see this web page. So you send a request, and that request you're going to encrypt. And you're going to use a key. And you're going to use this secret key. And you're going to encrypt the document so no one can see it. And then if it's going over the wire, no one's able to see it. And then only the server, if they have that same exact key, can they unlock that document and read it again. And the key to note here is both keys are exactly the same. So the server and the client have the same key, and that's why it's called symmetric encryption, because it's the same keys on both sides, and they need to be kept private. Because if someone has access to them, then they can also read the document. This encryption is a key aspect of the security provided, so I'll just give another better example of exactly how this works. So this is a ROT13 cipher, which is similar to the ROT10 cipher, where ROT is rotation, that was used by Caesar for his encryption of his messages. And here we're encrypting the word hello. We have the English alphabet. We move the English alphabet 10 over, so when we encrypt the H, it's a U, the E is an R, and the L is a Y. So hello becomes RB, which no one can read. But if someone has this key and they know, oh, they're using ROT10, then they can read the original message. The actual ciphers and encryption algorithms that are being used by TLS are thankfully much more complicated and harder to break than this algorithm. But the same basic principle that you have a key and you encrypt the message holds true. Okay, so we solved the problem of confidentiality through symmetric encryption, but not really. How do we both get the keys? So you go to a website you've never been to for the first time, and you say, can you give me the key? And maybe they just send you the key directly, but that's not going to work because that is unencrypted, and anyone could get that key, so the key is worthless. So how do we solve the problem that the client and the server need to have the same keys? And we solve that through another type of encryption called asymmetric encryption, also known as public key cryptography. So the main thing to note here that's different about the last picture is that both of these keys belong to the same person, and one is called the public key and one is called the private key, and they're no longer the same key. So now I'm the client and I want to talk to the server, and I grab the server's public key and I lock up the document, and then I send the server on, and the server can unlock the document, but only with the server's own private key. So even if someone else had the public key, which they probably do because it's public, that's why it's called the public key, and they have your publicly encrypted document, they can't read it. Only the server can read it. So problem 3, confidentiality and authenticity. So there's this public key. How is it public? Who is making it public and making it accessible? And if I get this public key, how do I know it's the correct public key that I'm encrypting for the right person, and that person is who they are? TLS's answer to this is the public key infrastructure, also known as PKI. I'm not going to go into much detail, but the main thing to know is that it's a large bureaucratic group of organizations that provide these keys. So the main body doing this is there's the certificate authority known as the CA, and it is the one giving out keys. And also there's the key and the certificate. So the certificate says this key belongs to this domain of this particular website. And then there are lots of other parts of the public key infrastructure that provide checks and balances to make sure that if maybe we found that a website was actually really insecure or the key didn't belong to the person that we thought it belonged to, that they could revoke that, or actually checking that you are who you say you are. So there are other parts of the organization providing these checks and balances. Okay, we still haven't quite solved the problem of confidentiality yet, though. So if we use asymmetric encryption now, which we can do because we have these public keys provided by the public key infrastructure, we still have the problem that asymmetric encryption is really slow and really expensive. It just wouldn't be very functional to have all web traffic going over asymmetric encryption. So now we get to the next part of the protocol. This is why we need the handshake to solve this problem, that we don't want to use asymmetric encryption all the time. And if you remember from the very beginning of the protocol, before we were talking about the data exchange, when you're actually going to see the content of your website, and the handshake is the step before that. So here's a scary looking diagram of the handshake. And we're going to start at the top. So at the client, which is you on your browser, and you want to see a particular website. So you send a message to the server that says, client, hello, I'd like to talk to you, and I would like to talk with you in an encrypted manner, and this is my capabilities to do so. And then the server sends you back a message called the server hello that says, hi, I'm glad you wanted to talk to me. Let's talk in this manner, and here is my certificate. And as you remember from before, the certificate includes the public key. And once the client has that public key, they are able to encrypt their next couple of messages. So these first two messages are actually completely unencrypted and not confidential at all. But then after that, once the client has the public key, they're able to start to communicate in an asymmetrically encrypted manner. And they don't want to talk asymmetrically encrypted very long because it's so slow and so expensive. So the first thing they do is they decide on the private key that they're going to use for the rest of this TSL connection, for the rest of the communication they're going to have. So they decide on the private key that for the symmetric encryption that's going to continue for the rest of the conversation. And they can do this now because they're already encrypted. So it's a safe channel to make this exchange. And yes, so once they have that, then they can switch over to symmetric encryption, and the handshake process is over. Okay, we finally actually figured out how TLS provides us a confidential conversation, but there are still other aspects of having a secure conversation that we haven't covered yet. And then next, we're going to go through all the different integrity problems that TLS helps us solve. The first one is integrity and tampering. Okay, so maybe I can't read your message anymore because it's completely encrypted, but maybe I could still switch it around and mess it up so it doesn't look correct anymore, and that would be tampering. So what TLS is doing, the tool it's using to prevent tampering, is called a hashing function, also known as a hash. And the hashing function is you take some input, so maybe the bit of content of your web page, you put it in, and then you get out this thing that looks like gobbledygook over in the bottom corner, and that is the hash. It's always going to be the same length. It's always going to be unique for whatever input you put in, and you won't be able to get the original input from it. And because it's unique and because it's this small identifier, well, you can use it kind of as a fingerprint. So it acts as this unique identifier for this content. So you know once you receive the message, and you receive it with a fingerprint, you know if the fingerprint doesn't match anymore that someone's tampered with it. So you can be assured of this integrity. And in the context of TLS, the name of the hash that we're going to use is called an HMAC, or a keyed hash message authentication code. And it's a little more complex than a normal hash that doesn't just provide the fingerprint, but from the word authentication, you can guess that it provides also an additional level of authentication that, yeah. Okay, so we fixed the problem, the first integrity issue, which is tampering, but that's for an individual for an individual message. When you're going to your client and looking at the web page, you're actually looking at many small data transfers that happened. You're not just looking at the result of one data transfer. So you can have dropping or replaying. So you could get one message multiple times, or you could be missing some messages. So you could be looking at a picture and there could just be like black splotches on it. And this can be done in the context of one individual request, or I could record your message and play it back like 2 years later in a totally another context. Either way, we do not have integrity anymore. So this is the least mathematical scary solution that TSL provides, which is just a sequence code. So we label the message. This is message 1, this is message 2, this is message 3, this is message 4. If you get 2 2s, you know you have a problem. If you're missing a 2, you know you have a problem. It's very easy to see that you no longer have integrity in your communication. And this is a little summary of what we've seen so far. So we have the sequence number and that plain text message that's unencrypted. We combined it and we make that message authentication code, and then we encrypt that together with that plain text and make the ciphertext, which is the encrypted text. And then we're passing all these parts forward. Okay, there's one more integrity issue that I'm going to go into, and that's truncation. It's actually just a special case of dropping. So what if you drop the last message? Do you really know, was that really the last message? Or did someone intercept my communication and I'm missing the rest of it? And here we have the explanation for why we have this third and last step of the TLS protocol, which is the shutdown. It's quite simple. Whoever wants to stop talking sends a close notify message. The other entity sends a close notify message, and then they ignore the rest of the messages until someone starts a handshake again. Okay, so now we finally have gotten to all parts of the TLS protocol and why they exist and how they're helping with security. And I'm just going to do a little quick summary. So we started with the handshake. And in the handshake, we're using asymmetric encryption to provide confidentiality. And we're able to do that with its public key encryption. So we need the public key infrastructure to distribute those public keys. And it does that to provide confidentiality as well as authenticity, that the website you go to actually is that website. Once we set up asymmetric encryption, we can start using symmetric encryption in the data exchange, which is also providing confidentiality. We also deal with issues of integrity here by providing sequence codes as well as hashes. And then when we're done communicating, to make sure that the process retained its integrity, we go to the last step, which is the shutdown. And that is the full TLS protocol. There's obviously many, many details that I am not getting into, but that's at a high level. So I know for me, understanding how something works and not just being like, oh, it's secure, makes me more excited about it. So maybe you're slightly more excited about SSL now and TLS. So what can I do? So you're all internet users, so this is all for you. What can you do? First step is just to be aware. Look for HTTPS in your URL bar. Am I actually using it? If you get one of those nasty messages saying, stop, this is insecure, don't be like 70% of all other internet users and click through. It's not a good idea. As well as Eva, in our first keynote yesterday, recommended using HTTPS everywhere, a tool that the EFF makes. And I want to plug it again and say, encryption is good. Use it more. This is a plugin that you can download to help you do that. Third advice for any internet user is update your browser. And you can go to the site on SSL Labs and run the client test and see if your browser is running the latest version of TLS. If it's not providing as much security as it can. And so, upgrade. Okay, I'm sure some of you are probably bored by my presentation because you're already developers or sysadmins, and I just want to take this moment to encourage you, if you are, to enable TLS wherever you can. And it's important that you don't just enable it, but you configure it correctly. And that's where a lot of issues have been in the past. So there are a lot of options that can be sort of opaque, and if you're not using the best ones, you may not actually be providing all of the security that TLS can provide. And I'm linking to in my slides, which will go out later on Twitter, to this deployment best practices guide, which I found very helpful in deploying my HTTPS-enabled site. So once I deploy, this presentation is available online via HTTPS on Meritz.rocks, which is the lovely domain I bought. And then I could check afterwards that I got an A rating and I set it up well, so it's actually quite secure. This is also a tool available through SSL Labs. And it's quite a nice tool, even for if you're just a normal internet user. You can go and you could plug in your bank's website, and you could see, okay, is it actually providing security, though it has the HTTPS, or did they do a bad job configuring it? And I'm going to wrap up there and say thank you. I hope you learned a little bit more about what it actually means to have secure communications on the web and how HTTPS is providing them. You can find my talk. I'll post it also on Twitter, both via HTTPS and not HTTPS, which was my originally hosting. Thank you.